Good morning, everyone. Thank you for coming. So today I will talk about my research. The title is on derivation of BPS equations of vortices in K-generalized Abelian-Higgs Model. By the way, my name is Ardian Nata Atmaja. I'm from Research Center for Physics, Derivation Institute of Sciences. I forgot to put my institute logo. Okay, so for introduction, so my discussion is mainly about a vortex. So what is mean by vortex? Vortex is kind of a solid. This is solutions of nonlinear equation of motion, but not only, but that's not only one of the requirements of vortex. It needs also to be a finite energy based on the theorem, and actually it needs to have electromagnetic charge. This is a consequence of Derivation theorem, and it is like a point object in three-dimensional field theory. Three-dimensional means three-dimensional space-time, so one time and two spatial dimensions. And in four-dimensional field theory, it becomes like a string object. So if you ever heard about a string, a cosmic string, that's kind of a vortex as well. And in mathematical terms, this vortex is an object with two co-dimensional space in general dimensions. Co-dimensional space means the remaining dimension of the object. Okay. Application of the vortex, there are many applications. One of is Nielsen-Olson vortices. This is apparently it describes the type 2 superconductor. This is based on Abelian study, and also it can be used in both Einstein condensation, quantum Hall effect, cosmic string, as I mentioned before, and also in for symmetry breaking phenomena. This is described by the model that I'll consider in this topic is K-generalized Abelian-Higgs model. Okay, in three dimensions, we have to put we have to use polar coordinates and try to solve the equations, the dynamical equations given by Lagrange. But this is second order equation, second order differential equation is really hard. So we need to find easy solutions, which is the first order differential equations known as BPS equations. Now there are three, as far as I know, three methods to find the first order differential equation. First is Bogomol's trick. This is a standard one, but this is sometimes too tricky. First order condition and stress energy momentum tensor. This is developed by Bazeia and al. From Brazil, and also on-cell method. This is developed by me and one of the my co-author from English University. This method we developed, we call it on-cell method. Now, from the on-cell method, we learn there are characteristics of the vortices, that the energy of the vortices in some model is total derivative of the effective field. Now, surprisingly, all the vortices in different models could have the same formula for energy density. Now, the energy density is given by this. This is actually the total energy, but the energy density is the Q itself. And now we come to ask whether it will be the same for other models too. Now, this is the K-generalized Abelian-Higgs model. So this is the Lagrangian, and the matrix we choose the diagonal with plus times and minus in the spatial coordinates. Okay. So if you are familiar with field theory, then also this theory you probably know all this, F mu and phi. And the answer we take is like this: Fr and epsilon I and theta, and we take A theta to be like this, and we consider only the static solution. with the radial gate, you take radial gate with where AR is equal to 0. And we get the effective Lagrangian given by this in terms of F and A. Next we choose the answers for the BPS energy density, the Q, the one that I gave before, this Q. So we take the answer to be variable function depend on F and A, and then I write from this BPS energy density I can derive what I call as Lagrangian, Lagrangian BPS Lagrangian, and then I match the BPS Lagrangian with the effective Lagrangian, with this effective Lagrangian. Then I split the equation into two equations, and solution for the first equation is given by this equation. This is known as the self-dual conditions in solutions. And yeah, so we need to solve the other equation. Now, the one is proposed by the first paper in this K-generalized Abelian-Higgs model is by adding some terms in the Lagrangian. So then you can get the second equation to be like this. Okay, and then they get the solution. The additional term that they put is there's also additional field. This W function of F is effective field of the scalar, and they get this solution. Okay, and then they also get a constant equation, something like this. Okay, and for a special case where they stick the small w equals 1, p equals 0, h equals u, and big W, it gives a big W, the function f squared plus 2w, and they get the solutions where now they have this f function as this of this field is actually must be smaller than 0, and it should be a C number. Okay, I have 1 minute. So I give now alternative solution where you don't have to add additional terms to your Lagrangian. You don't have to put field, but you just choose the second equations without adding any additional terms. It will be like this, and then you get some this F, something like this, and you get the BPS equations like this, and this is for strain, and then you derive some kind of semi-active Lagrangian, and from this the semi-effective Lagrangian, I call it semi-effective, you get like Euler Lagrange equation for A, and by taking the key F similar like this, and then you get this Euler Lagrange equation become like this, and this is similar to one that derived before using the self-dual solution. Okay, this is actually the derivative of the circuit one that I showed you. Okay, so I don't put any conclusion, and thank you.
Sir, my name is Christopher. I am from the Department of Physics of Indonesia. My question is, with all of those equations you derive, is there any example of particle or material that follows Ardian model?
Well, this is a new model, so we don't have, so far as I know, we don't have realizations of this in real life. So, well, we don't know. I mean, maybe you could try to build some system that mimics this model, or maybe there's another phenomena you try to see. Maybe it can be described by this model. But so far, we still have no clue what kind of system that described by this model. Because there are so many free parameters. There are so many free parameters especially in the Lagrangian. Here I can put any function of h, here I can put any function of k and also w and even v. So it's kind of so many freedom.
Okay, thank you. You can give a word for and actually we have the last presenter is Muhammad Haitham Hatibi. Okay. Because he is not coming, so the first parallelization for today